Hello guys, welcome back to our class. Welcome back to our channel. So, welcome back and now let's proceed to our next lesson which is about the stress strain behavior of ductile and brittle materials. What are ductile and brittle materials? So that is what we are going to learn for this lesson. And for our goal for this lesson as well, we have to define ductile and brittle materials and also understand the behavior of ductile and brittle materials in a stress and strain diagram. Okay? What are ductile materials? And what are brittle materials? Sige, ato unahon ang brittle materials kay I guess you are familiar with brittle materials. So what are brittle materials daw be? 'Di ba? For example, for brittle materials are glass, concrete, I guess, and the like. 'Di ba? Nga na ang mga brittle materials. So, therefore, if you are going to define brittle materials are materials that will create a fracture or it will break whenever bisan gamay lang kaayo nga strain ang ni-deform ana nga object. So again, brittle materials are materials that fractures even with very small strains. Okay, di ba? Sa imong glass, di man mo bend ang imong glass. Ang imong glass, bisag gamay lang kaayo nga pagka bend, mubuak siya dayon. Or gamay lang kayo nga strain, mubuak dayon ang imong glass. And ductile materials are the opposite of brittle materials. So therefore, defining ductile materials, they are basically materials that can be subjected to large strains before it breaks. It doesn't mean that ductile materials are stronger than brittle materials. Kay, pwede man nga ang atong mga brittle materials, taas pod kayo siya ultimate stress nga pwede niya makuha before siya ma-break. Compared sa atong ductile material nga, niinat siya pero gamay lang nga stress ang iyang kaya. So, mao lang to ilang difference. Ductile materials, they can be subjected to large strains before they break and before they fracture, and brittle materials dili nila makaya ang mga dagko nga strain and they will break immediately when naay gamay bisan gamay lang nga strain. Now let's focus ourselves on the ductile materials because ductile materials are specified by their percent elongation and percent reduction in area. Kaya di ba, ang atong mga ductile materials, maka-handle man sila og large nga strain. So, naatay yung mga percent elongation and percent reduction in area. For us to be able to know how well a material can be subjected to strain before it breaks. Okay? So, how can you determine the percent elongation or percent reduction of area of an object? Okay, so you have this percent elongation. And basically, the equation of your percent elongation is just simply your LF minus LO over LO times 100. What can you notice on the formula? I think you are familiar with this equation. LF minus LO over LO, because this equation is actually your equation of your normal strain. Diba? And para makuha nimong percent elongation sa usa ka material or sa ka specimen, all you have to do is to multiply your normal strain times 100. So, mao lang na ang imong pagkuha sa imong percent elongation. So, sige, ato daw ni tan-awon nga example sa atong kaganiha nga example. So, to get the percent elongation of this steel nga stress strain diagram nato, ato tan-awon ang iyang fracture nga strain. Okay? So, ang iyang strain sa pag-fracture niya. And that is 0.380 ang atong strain. So therefore, the percent elongation of this steel nga material nga atong example earlier is 38%. Yung ana lang. Okay? So, ato ta sa percent reduction in area. Percent reduction in area is just the same sa concept sa imong percent elongation. Pero, karon, this is just equal to your initial area. Take note, initial, kaya sa atong elongation final man to. Initial area minus final area over initial area. Ana lang. Kaya nganong ingani man, kay ang atong final nga area is always smaller compared sa atong initial area, especially when it is subjected to tension, right? So, para positive ang atong percent reduction, the initial should be before the final. So mao lang na ilang difference sa atong elongation. Ang final nakauna sa elongation, ang sa reduction, ang initial lang nakauna. Okay? Yung ana lang. So, ang atong AF, this is your area before it fractured. Area during the fracture, before or during the fracture. And ang AO, ang initial area before nimo siya gi-subject into tension. Ana lang. Now, so there are some times that you have a material that does not have a well-defined points. Just like this one. Dili nimo ma-notice kung asa ang yield stress, ang proportional limit, and blah blah blah. So we have this rule. And this rule is only applicable for your yield stress. And unsa man di ini nga rule, mao ni atong giingon nga 2% offset. So since dili man defined ang imong curve and dili ka makalocate kung asa ang yield stress ana, then maghimo ka og offset diri sa 2% offset, or that is 0.002 nga strain. Okay? So, asa man kung tayo ni ato 0.02, ato isulti nga diri mo ni atong 0.002 nga strain. Okay? Naghimo tag ana nga offset from the origin, and then ato siya gi parallel aning atong line. And kung asa na siya nagtagbo, dira malocate ang imong yield stress. Okay? Dagdag kaalaman, nga na lang na siya. So, kung naa kay curve nga dili defined kaayo ang iyang mga points, then you can use this 2% offset in order for you to determine the yield stress. Okay? Now, let's go back to brittle materials. Again, brittle materials only exhibit little to no yielding before it breaks. Okay? So we have here some example of gray cast iron daw, and these type of materials, bisan naalang siya gamay kay nga crack, then that very small crack will just immediately get bigger and bigger, and then the material fractures. Okay? So, ingana itong mga brittle nga mga materials. Ingani, when are brittle materials used and when are ductile materials used? Sir, nganong magamit man tag mga brittle material? Nganong dili ductile material man tong gamiton kay para kay ang kani mga ductile material nindot ni sila because they can be subjected to weathering, they can be subjected to forces that are not expected, like for example earthquakes, and mo-adjust sila sa kung unsay stress nga gi-applyan na nila. Unlike sa mong brittle nga mabuak na dayon, but kano sa magamit ang atong mga brittle materials. Brittle materials can actually be used sa kanang mga structural members that are subjected to compression. Because brittle materials are good in compression, they are more resistant in compression compared sa atong tension. That is why we have our structural members, usually we have this concrete. Kaya ang kaning concrete, they are usually subjected to compressive nga mga stress. Diba? That is why we have columns. Because columns are compressive stress nga mga structural members. and steel. Steel are ductile materials, therefore, they are good in tension. Ana ha? So tension. So ang kaning atong mga ductile nga mga materials, they are usually good at tension, and your brittle materials are good at compression. So that is why your columns, your concrete is usually reinforced with steel bars. So para may gamit para ang atong mga columns is good in both tension and compression. Di ba? Nakabantay mo sa anang atong mga maning cross section sa atong column. Nya na siya steel bars dira. Nakaingana na siya. Di ba? And we have these steel bars naka-reinforce na siya para ang atong mga columns is both good in tension and compression. Okay? So, ingana lang. Let's define stiffness. What is stiffness? Tikig. Ang stiffness actually is based on the modulus of elasticity of a material. Let's say, for example, I have a material nga mao ni ang iyang proportional nga line, and nanapod ko another material nga mao ni ang proportional nga line. So which of these materials is stiffer? Ang kanang stiff nga materials, they are usually stiff materials have higher modulus of elasticity. So asa may mas taas ang modulus of elasticity ani? Ang mas steep ug slow. Kay di ba rise over run. So kung mas dako ang imong rise compared sa imong run, that has a bigger value. But kung mas dako ang imong run kaysa imong rise, then probably mas gamay ang value sa imong modulus of elasticity. Therefore, stiff materials like dako ang iyang stress nga subject pero gamay lang iyang strain, mao na atong mga stiff materials. Probably brittle materials are stiff materials. But kanang mga brittle materials wa jud na ay almost no strain jud na sila. Pero kung mayroon kag stiff nga mga materials, they can be subjected to strain pero dili sila maguba, dili sila ma-fracture. But gahi lang sila i-deform. Pero kung dili stiff ang atong material, these are for example sponges or rubber. So bisa gamay lang ang force, dako ang iyang strain. Okay? So the higher the modulus of elasticity of a material, the stiffer that material is. So arita, last. Let's talk about strain energy. Strain energy is just basically the energy the material obtained or the material generated when subjected to strain. Di ba kay we learned that magbutang kag force and then i-multiply siya og distance that creates work. Di ba? And materials or specimen or objects in which their dimensions were changed, then na work nga na-create ana. Then therefore na energy nga na-produce ana nga material. Okay? So that is what you call the strain energy. And we have this what you call the strain energy density. And we have this formula, strain energy density is equal to 1/2 stress times strain. We won't be dealing with how this equation was generated, but let's just deal with this one nga. Mao lang na ang atong formula sa atong strain energy density. But if our material behaves linearly elastic and we apply the Hooke's law, then we will get that the strain energy density of an object is 1/2 stress squared over the modulus of elasticity. And this one is just created because of the equation stress over strain. Okay? And we have two modulus of Chuchu, which is under your strain energy. Your modulus of toughness and modulus of resilience. These two moduluses are basically strain energy. But they have a difference. Unsa may difference anang atong modulus of resilience ug modulus of toughness? So basically, when you're talking about modulus of resilience, ang modulus of resilience na to is actually the area na na-cover sa atong proportional line. Okay? So ang area ani, unsa man? So modulus of resilience, your UR is equal to the area of the triangle, 1/2 times base of strain nga imong PL times your height of imong stress PL. So that is your modulus of resilience. But sa imong modulus of toughness, that is just basically the whole area of the curve before it fractured. So mao na ang atong modulus of toughness. And unsa ang pag-solve sa modulus of toughness, it will vary. Okay? Imo lang ko ang area sa curve, then that is your modulus of toughness. Understood? So let's have an example. Only one example because na-stress na inyong sir, kapoy nag-discuss, gisipon pa gajud si sir. So please bear with me. And for the other problems, just study it with yourself and just learn the topic, and I hope that you have learned it sa akong discussion. So we have here an aluminum alloy that is used for making aircraft parts. And a specimen of that aluminum alloy is taken and it is subjected to a tension test. And ang specimen daw gi-stress, gi-applyan siya og stress until 600 megapascals. Okay? And determine daw the permanent set. Sa ganitong permanent set, mao na ang iyang strain once ni labaw na siya sa iyang proportional ay sa iyang elastic nga behavior. So naana siya sa iyang plastic and then imo gi-remove ang stress, wala siya ni balik sa zero, so the distance mao na ang permanent set. Okay? And find the modulus of resilience both before and after the load application. So ang atong buhaton una, tanaw ng curve, and then naa siya proportional nga line, and then ingana siya. What we are required is the permanent set, perma set na lang, and then the modulus of resilience. So mao na tong gipangita. Ang giingon diri, given sa atong stress strain diagram diri sa atong problem, we have here your proportional limit, your proportional line or your yield stress of 450. Okay? And we have this here 600 KSI. Di ba kaya ang atong specimen giload siya until 600 KSI o niya gi-stop ang operation. So na asya diri ni igo dira nga point. And then, di ba kay elastic behavior pa man siya diri. But after sa iyang proportional nga line ni yield na siya, then once gani moabot na ang atong strain diri, inigbalik ana niya, dili na siya mobalik diri sa original, but it will create a permanent set which is ato nahibaw-an parallel siya sa atong kani nga line. Okay? So this is your permanent set. Perma set. Okay? So, how will we determine the permanent set? Ato dapat hibaw-an kay ang value diri. Kay mao na ng permanent set. Pero unsa man nato paghibaw-an ang value? You are given that the strain in this point is 0.023. And the strain in this point, wala na sila nagkatagbo silang permanent set ha. Pero ito isulti nga 0.006. Okay? Unsa man na pagkuha. Sige, di ba naman tayo ani nga triangle? Nata ani nga triangle. And we know the slope. We can know the slope. How can we know the slope? We should know this slope. Di ba? And if we know this slope, then we can determine the length of this one and then minus it to get the value of this point. Okay? Sige. So, ato pangitaon una ang modulus of elasticity. The modulus of elasticity is given, which is ang kaning 450 ang atong kuan, rise 450 over ang atong run, which is 0.006. So, take note, this is not KSI na di ay, but megapascals. And this is mm per mm. So, we have your modulus of elasticity of 75,000 megapascals or 75 gigapascals. Okay? So, mao na itong modulus of elasticity. And we can apply it in this triangle because we learned that the modulus of elasticity of the material is always the same bisag subject na siya ag load. Okay? Now, ato pangitaon ang kaninga length. Let's call this length as x. Okay? And we know this height. So, and we know the equation is equal to stress over strain. So, ato gipangita kay kaning x. So, mo ning atong x. Okay? So, x is equal to stress over modulus of elasticity. So, pila ang imong stress? 600 over modulus of elasticity of 75 gigapascals. So, therefore, that is 0.008 millimeters per millimeters. So, ang imo lang buhaton, kay di ba mao man ning 0.008? So, to get your permanent set, which is the distance from here to here, imo lang buhaton is 0.23 minus 0.008. So, perma set is equal to 0.023 minus 0.008. So, that is 0.015 mm per mm. Okay? So, that is your answer for your permanent set. Pero wala pa tanahuman because we are also looking for modulus of resilience before and after the loading. So, maghimo ta sa before. Before. So, mo ni ang gamay ang before. Di ba? We learned that the modulus of resilience before is equal to the area of this triangle. So, 1/2 times base, which is 0.006 times height of 450. So, the answer is 1.35. Unsa unit ani? Unsa unit ani first? Megajoules per meter cube. Just imagine nga manipulate ang equation sa atong megapascal and then you can just convert it into this kind of unit. Okay? So this is your answer for your before. How about your after? Strain energy density after. 1/2 times base na pod of 0. Di ba na, ibaon na to, 0.08 kaganiha sa ito pag-solve. And then the height is 600, which is equal to 2.4 megajoules per meter cube. Take note, the modulus of resilience of the second, of the after is the area of this one. Wala ko nagbutang diri nga 0.023 because it starts from here to here. So, mao ni imong gikuha nga triangle kung 0.23 imo. But this is only 0.008. That's why, mao na ako gibutang dira. And this is your strain energy density or modulus of resilience on your after nga loading. Okay? Understood? So, sayon lang kaya itong lesson karon. A summary of our lesson for this time, we have dealt with the definition of your brittle and ductile materials. I hope that you have learned the difference ng duha. And we also have seen the behavior of brittle and ductile materials in the stress strain diagram. And also we have learned modulus of resilience, modulus of toughness, and strain energy density. So I hope that you have learned all of these things in this topic, and if you haven't grasped the concept yet, then watch this video again and again or read some other resources. Okay? So thank you for listening and thank you for your time. So see you on our next episode.